Good morning. Welcome to measure theory. Last time we stopped in the middle of a proof again, so we started proving lemma 515, which said that Cauchy sequences converge in LP, and in the new LP spaces that we defined, and we proved the case P equals infinity last time. And what's left is to prove the case P between 1 and infinity. And I said this last time, the strategy of the proof in the case P equal to infinity was to start with the L infinity estimate, the L infinity definition of Cauchy sequences, then pass to pointwise estimates, then conclude that the sequences Fn of x pointwise are Cauchy sequences in R, and this gave us a limit pointwise. And this way we could define a limit function and then show that this is an LP. And the general strategy in the case P between 1 and infinity is going to be exactly the same. Just the details will be slightly different. So in the case P between 1 and infinity, the start is, so start with a Cauchy sequence in LP. Then, because of the definition of Cauchy sequences, what we can always do is the following. Choose a subsequence. Fnk such that the LP norm of Fn k plus 1 minus Fn k is less than 2 to the power minus k. So we can always find such a subsequence just by the definition of Cauchy sequences. And this is our starting point. And now we pass from this LP estimate to a pointwise estimate. So we define the following. Function g of gn of x to be the sum from k equals 1 to n Fn k of x minus, actually Fn k plus 1 of x minus Fn k of x, absolute value. And now we study this function g. So, where Fn k plus 1 and Fn k are finite valued representatives of these classes of the Fn k, because we want to compute this difference, then they're not allowed to be both infinite. So just choose some finite valued representative and then you can do this. Okay, and now this function g has got several nice properties that we can see immediately. The first one is the LP norm of Gn is bounded by sum over 2 to the minus k, right? Sum k equals 1 to n 2 to the minus k, which is bounded by 1. So the LP norm of Gn is always bounded by 1, no matter what n is. And also, Gn are always non-negative and increasing. Increasing means they're an increasing sequence of n. Right, because it's a sum of non-negative things. So as n increases, Gn increases. Okay, and well, if you have a sequence of non-negative increasing functions, what do? You use the monotone convergence theorem and get a statement about its limit. So because this sequence is non-negative and increasing, we can always define its limit, call it G. It might be infinite at some points, but if we allow this, then this always exists. And now by the monotone convergence theorem, the LP norm of G is also bounded by 1, because the LP norm of G is the limit of the LP norms of Gn, which are bounded by 1, independent of n. Okay, so we have this function G, which is bounded by 1 in LP. So in particular, G is in LP. And this implies that that G is in fact finite almost everywhere. Okay, so we started with just an increasing sequence. Then we defined the limit, which we know we could do because it's increasing, but we didn't know whether it could have been infinite everywhere. But now we know that it's finite almost everywhere. Okay, keep this in mind. And now we're going to start deducing stuff about the sequence f and k. So the first claim is this subsequence fnj, pointwise, fnj, the sequence fnj of x is the Cauchy sequence in R for almost every x in the measure space X. Okay, so this is what I said. We start with the LP estimate, then we pass to pointwise estimates, which allow us to get, to deduce that pointwise these sequences of values of f and j are Cauchy sequences. So, and to prove this claim, we use these functions gn and g. Okay, so we want to show that this is a Cauchy sequence. So let m and k be natural numbers. Then we have the following estimate. So if we write down f nm of x minus f n k of x, absolute value. Right, so we want this thing to be small if m and k are large enough. That's what Cauchy sequence means. So using the triangle inequality, this difference can be estimated by just inserting all the other f and j between f and m and f and k. So this is bounded by f n m of x minus f n m minus 1 of x plus and so on until we arrive at f n k. So the last one will be f n k plus 1 of x minus f n k of x. Okay, so this just follows from the triangle inequality. And now compare this right-hand side to the definition of G. So Gn was defined to be this finite sum, and G was defined to be the infinite sum. So on this right-hand side, we go from f and m down to f and k, and then below f and k, below nk, there are no more terms. So the first few terms of this sum are missing, basically, in this right-hand side. And on the left, there are terms missing as well, right? In the definition of G, and this sum would go to infinity, but here the sum only goes to nm. So this right-hand side can be estimated by G minus G k minus 1. Right? So G is the infinite sum. So it includes all these terms from k equals 1 to infinity. If we subtract gk minus 1, then the first k minus 1 terms of this sum are missing. But here they're also missing. So this difference g minus gk minus 1 includes all these terms plus everything on the left, plus everything where the index is larger than nm. Okay, so that's why this g minus g k minus 1 is an upper bound for these terms. Okay, but now we know that g minus gk minus 1 goes to 0 for k to infinity because g is the limit of gn. Okay, so first this inequality holds there should be g of x and gk minus 1 of x, sorry. And this holds for almost every x and for all m, right? Because here it doesn't matter how large I choose m, because g of x includes everything on the left-hand side. So, and this holds for almost every x, because I can do this estimate whenever g of x is finite, right? And g of x is finite almost everywhere. So almost everywhere, this estimate makes sense. Okay, but now, as I said, this goes to 0 as k goes to infinity. And this implies that f and m of x minus f and k of x can be made arbitrarily small by choosing m large enough and choosing k large enough, which means that it's a Cauchy sequence. Okay, so yeah, I've given this null set a name now. So fn of fnk of x is a Cauchy sequence in R for every x in the measure space X minus some null set E. Okay. Okay, but if it's a Cauchy sequence in R, then it has a limit in R. So we can make the following definition. We can define a function f of x to be the limit k to infinity of characteristic function of x minus e times f and k of x. Right, this function on the right hand side, this sequence on the right hand side converges for every x, because for every x in x minus e, this sequence is a Cauchy sequence, so it has a limit, and for every x in e, this prefactor is 0, so this product converges as well. So this definition makes sense. Okay, so we have a candidate for a limit function in LP now. And now what we have to prove is that, in fact, f is in LP, and that the LP norm of f minus fn goes to 0. Okay, first what we know immediately is that this defines a measurable function. Just because the right-hand side is, the sequence on the right-hand side consists of measurable functions. And we know that measurability is preserved under taking pointwise limits. So this defines a measurable function. And in addition, we know the following two things. If we look at the difference between this chi x minus e f and k and f, then this difference is bounded again by g minus g n k minus 1. That's by this estimate again. If we take this inequality and send m to infinity, then now this left-hand side becomes f, and this right-hand side just is independent of m. So we have f minus f and k is bounded by this. So we have this inequality almost everywhere. And this g minus g and k minus 1 is less than g, of course, just because this is non-negative, this gn. Okay, so this holds almost everywhere. Okay, but now g, we know that g is in LP. So this difference is bounded by an LP function, which means that this difference has to be an LP function as well, because it's non-negative. So chi x minus e f and k minus f is in LP. But we started with the sequence in LP, right? So if this difference is in LP, then f has to be in LP. Okay, so this is the first thing we know. We have this uniform bound on these sequence elements. They're bounded by G. And as a side product, we got f is in LP. And then second, we know that just by definitions that this difference goes to 0 pointwise. Chi x minus e f n k minus f to the power p goes to 0 almost everywhere. Just because f was defined to be the limit of this pointwise. So this certainly goes to 0 almost everywhere. Okay, but now we have pointwise convergence, and the sequence is dominated by a function in LP. So we can use the dominated convergence theorem and apply it to this sequence. And the dominated convergence theorem tells us that then the integrals of this go to 0 as well. So but the integral of this is just the pth power of the LP norm. So we can conclude that the LP norm of this difference goes to 0. Which is of course the same as saying that now I'm just translating this to equivalence classes. So the equivalence class of this chi x minus e f n k is the same as the equivalence class of f n k. And here we have the equivalence class of f. So we concluded that for the subsequence fnk, we have a limit f, and we have LP convergence of fnk to f. So the class of fnk is the same as the class of this, because they're equal almost everywhere, right? The only thing that's where they might be different is the set E, which has measure 0. Okay, so that almost finishes the proof, but not quite, because here we only have a subsequence of fn. But we want to show that the entire sequence fn converges. So we have to do a little more work, but not too much. Okay, so keep this in mind. Okay, for the convergence of the entire sequence, let epsilon be positive, and take n and nk natural numbers such that norm fn minus fnk is less than epsilon. Right, so up to here, nothing spectacular has happened yet. I've just used the fact that the sequence fn is a Cauchy sequence. And that's why I can always make the difference between these two sequence elements less than any given epsilon. And now we look at the difference between fn and f. In LP. So So this is what we want to go to 0. Okay, so this difference Fn minus F, in this difference we can use the triangle inequality again and sneak in a sequence element Fnk. So this is bounded by the LP norm of Fn minus Fnk plus the LP norm of Fnk minus F okay, but now this Fnk minus F goes to 0 because we've chosen the right subsequence, so we can use the fact that this goes to 0. So if we send nk, well, first, yeah, and this is less than epsilon, right? This first term. So first we can conclude that this is less than epsilon plus the second term. And now we can send k to infinity, and then this term goes to 0. Okay, and now we found that if we choose n large enough, then the LP difference between Fn and F is less than any given epsilon. So this is precisely the definition of convergence, right? So we're done. So from the convergence of the subsequence and the fact that it's a Cauchy sequence, it immediately follows that the entire sequence converges. Okay, are there any questions about this proof?
On the middle board,
Yeah.
right at the bottom, you've got less than or equal to g of x minus gk minus 1 of x.
Yeah.
There. When we're saying it tends to 0, is it implied that gk minus 1 tends to g of x? Sorry, I moved it off.
Yes, because g was defined to be the limit
Okay.
of the
Okay.
gn. So this goes to 0 by definition. At least almost everywhere. At least everywhere where g of x is finite. Yeah.
I'm a bit confused by this like n and nk stuff, because are you saying there exists n and k, or are you saying for all n large enough there exists nk? Because
I'm using the definition of Cauchy sequence, which means that for every epsilon positive there exists some capital N such that for every n and m larger than capital N, one has that Fn minus Fn less than epsilon. Right, this is the definition of Cauchy sequence. And now, okay, someone gives me an epsilon, and then I can choose capital N such that this holds. So in particular, if n and m are both large enough, I can choose them however I want. So I can choose m to be one of the nk, as long as it's larger than this capital N. And then n, I can choose any number which is larger than this capital A, and I will have this estimate. So basically I'm just using this definition and replacing m by large enough nk. So yes, n and nk both have to be large enough in order order for this to hold. But I can always do it because it's a Cauchy sequence. Did that make sense?
I think what I still don't understand is then why you can take the limit with the nk, because yeah.
I think he's using the specific subsequence that we did right at the start. Is that correct?
Yeah, but then so you bounded fn minus nk by epsilon.
Yes.
And then you move the...
Then I move the nk, but I'm only making it larger. But this holds for every nm larger than a fixed capital N. So I can always make n and m larger and still have this bound.
Okay.
For a Cauchy sequence.
Oh, okay, yeah.
So I can always make stuff larger and have the same bound. I'm not allowed to make it smaller. Okay. Any more questions? Okay, so this was probably the most complicated proof of the entire lecture so far. So yeah, feel free to ask more questions. Also later if you find any more questions. If there are no more questions right now, okay, let's continue. And okay. So from the proof of this lemma, we immediately have one nice corollary, which comes in handy sometimes. And goes like this. Let P be between 1 and infinity, and assume that Fn converges to F in LP. Let Fn be a sequence of representatives. Of this sequence of classes Fn, then there exists a subsequence Fnk with Fnk converging to F pointwise almost everywhere. Okay, so in short, if a sequence converges in LP, then a subsequence converges almost everywhere. That we can always conclude from the proof of this lemma, right? We explicitly constructed such a subsequence, more or less. Yeah, so this can often come in handy, but it's important to realize that we can only conclude pointwise convergence for a subsequence and not for the entire sequence. And there are counterexamples that show this nicely. And we'll see one of these counterexamples now. Okay, so first, very quickly, the proof of this is just take fnk from the previous proof. Okay, and the following remark just says what I just said, the subsequence in this corollary cannot be omitted. At least when p is less than infinity. If p is infinity, I mean, convergence in L infinity implies convergence almost everywhere because the essential supremum has to go to 0. But for p less than infinity, this subsequence requirement in this corollary cannot be omitted. And there's a simple example that shows this. So there exists a sequence of functions which converges to 0 in every LP for p less than infinity, but does not converge pointwise for any point. And the sequence looks like this. It's quite simple. So take the real line, take the interval from 0 to 1, and then the sequence looks like this. The first element is just a step function between 0 and 1/2. The second element of the sequence is the same step but moved to the right. So f2 looks like this. Okay. And then f3 okay, so this point is 1/2, where f1 ends. And now we divide the interval into 3 parts. So we have 1/3 and 2/3. And then f3 looks like this. Okay, so it's a narrower step. And it starts between 0 and 1/3. f4 is the same step moved to the right by 1/3. f5 is the same step moved to the right by 1/3. And so on. And the next element of the sequence will be, so f6 will be a step of width 1/4, which is between 0 and 1/4, and then it's moved to the right again. So this sequence consists of steps which swipe out the interval and then become narrower, and then swipe out the interval again and then become narrower, and so on. So this sequence clearly converges to 0 in every LP, just because the area under this curve goes to 0, right? Because it becomes narrower and narrower and the width goes to 0. So that's why this converges to 0 in every LP. And then it doesn't converge pointwise for any point x. Because if you choose an arbitrary point x in this interval, then fn of x will always alternate between 0 and 1, right? Every time the step crosses x, it will be 1 again, and then 0, and then when it crosses again, it will be 1. So there's no x for which fn of x converges. So this is a counterexample that shows that the subsequence requirement cannot be omitted. And also from this example, of course, there exists a subsequence, right? You can always take this first step, for example. So you can take f1, f3, and then whatever the next one is, f6. And this gives you a subsequence which converges pointwise almost everywhere, because it's just this one step that shrinks and goes to 0. Okay, so this is one nice corollary. And it's a good thing to remember this counterexample. Okay. Okay, the next theorem is just a summary of results that we've already got from these lemmas. So let X sigma mu be a measure space. And P between 1 and infinity, then LP of X sigma mu is a Banach space. Right, which just means that it's a normed vector space and Cauchy sequences converge. And we've shown all this in the lemmas. So the proof of this is just consequence of lemma 5.12 and lemma 5.15. Okay, and we conclude this section with a couple of examples for LP spaces. The first one, just so you've seen this if P equals 2, so the space L2 is actually a Hilbert space, not just a Banach space. Because if we define a scalar product in the following way, f comma g is defined as integral f times g d mu, then the L2 norm of f is precisely the square root of the inner product of f with itself. Right, so in the case L2, one can define this scalar product, and then the space becomes a Hilbert space. And we can, in particular, I mean, now that we know that LP spaces are Banach spaces and L2 is a Hilbert space, we can throw all of functional analysis at them and get lots of new statements about these spaces. That's why it's so useful to know that these spaces have this structure. Okay, the next example. If we take the particular measure space x sigma to be the natural numbers with the power set and the measure to be the counting measure, then the empty set is the only set of measure 0, right? Because the counting measure counts the elements. So f equals g almost everywhere is the same as saying that f equal to g everywhere. So in this case, the LP spaces look particularly simple. Every equivalence class just has one element. So the new LP spaces are practically the same as the old LP spaces in this case, for this measure space. And moreover, if p is less than infinity, then LP is just the set of functions from n to r such that the sum n equals 1 to infinity